x equal to norm of x equal to supremum of mod xi. We prove that completeness of infinity. The let inner product of x power m, inner product of x power m equal to 1 to infinity be any Cauchy sequence in L infinity. Since each xm is a sequence of scalars, we shall write x power m equal to x1 whole power m, comma x2 whole power n, etc. xn whole power m. Let us epsilon greater than be given. Then there exists a positive integer n such that L comma m greater than or equal to n. That implies norm of xm minus xi less than epsilon. So that implies maximum of xi whole power m minus xi whole power t. Norm of x2 whole power m minus x2 whole power 1 such that so on x modulus of xn whole power m minus xn whole power n less than infinity. So that implies xi whole power m minus xi whole power n less than epsilon. Where I equal to 1, 2, such that so on n. This shows that for field I, inner product of xi whole power m m equal to 1 to infinity is a Cauchy sequence of real numbers. Hence, R is a completed. Is must converges to some Zi belongs to R. Let Z equal to Z1, Z2, etc. Zn. So, norm of x power m minus Z norm that is equal to maximum of maximum of x power m minus Zi. X power m minus Zi, comma x power n whole power m minus Zn, and so on tends to infinity as m tends to infinity, tends to 0 as m tends to infinity. Hence x power m tends to Z as m tends to infinity. So thus Cauchy sequence inner product x power m converges to Z. So that equal to Z1, comma Z2, etc. Hence L infinity is a Banach space. Hence proved. Next definition 2.4.1. 2.4.1 definition, most important for exam point of view, this one. So definition, let x comma d, y comma d dash be two metric spaces. So let there exist a map f of x and 2. So f bar of x equal to x, that is f of x is dense in x dash. Then we say x comma d can be embedded in x dash d dash. So theorem 2.4.2 theorem. So every metric space can be embedded in a complete metric space, which is called the completion of the given metric space. So proof. So we can prove this one. So let X be a metric space with metric D. Let B be the set of all Cauchy sequence in X. So we now prove that for any Cauchy sequences. So X equal to Xn and Y equal to Yn. Limit n tends to infinity D x comma Yn exists. So we have D x comma Ym less than or equal to D xm comma Ym plus D xn plus Yn Yn plus D Yn comma Ym. From this we get so modulus of D xm comma Ym minus D of xn comma Yn modulus less than or equal to D xm comma Yn plus D Yn comma Ym. So most important theorem, this one, for example, point of view, since xn comma Yn are Cauchy sequences. It follows that dxn comma ym tends to 0 and dyn comma ym tends to 0 as n comma m tends to infinity. Thus alpha xn comma yn is a Cauchy sequence of real numbers. Hence, so converges. So limit n when limit d of xn comma yn exists, we define a relation on B as follows. So xn equal to yn means two Cauchy sequences are equal. Two Cauchy sequences are equal. So this two Cauchy sequences are as follows. So B follows xn equal to yn if dxn comma yn tends to 0 as n tends to infinity. Okay. The B is partitioned into disjoint equivalency classes. Disjoint equivalency classes. Equivalency classes means this is in relations and functions. Relation chapters. This is a relation chapter. The partition into disjoint equivalency classes. So now let X bar be the set of all equivalency classes in B. So in relation, relations we have a identity relation, symmetric relation, reflexive relation, etc. So D on X bar as follows. So alpha cap X cap comma Y cap equal to limit n tends to infinity D xn comma yn. Xn comma yn. So then it can be shown that D infinity is a metric on X bar if X cap respectively a Cauchy sequence xn. Then for epsilon greater than 0, there exists an integer neta epsilon such that D X cap comma xm star less than epsilon for all n is greater than or equal to n epsilon equal to 1, where xm star represent the sequence xm comma m etc. m. We now show that X cap is complete. That implies D cap xn star comma xn cap less than 1 by n. Then m comma n large. So xn star xn minus less than or equal to D xm star comma xm cap plus D cap. So xm comma xn star plus D cap xn cap comma xn less than 1 by epsilon 1 by m plus alpha cap xm cap comma xn cap plus 1 by n. So therefore xm cap is a Cauchy sequence. It follows xn is a Cauchy sequence in X from the inequality D cap X cap xn cap less than or equal to D cap X cap xn star plus D cap xn star comma xn star. It follows that D cap X cap comma xn tends to 0 as 10 tends to infinity. Thus X is complete. This completes a proof. So what is Banach here? Chapter 2. Unit 2 is a Banach spaces and functional analysis. Functional analysis is the most important chapter. So concepts. What are the concepts are there here? 2.3.1 definition. 2.3.1 definition. 2.3.1 definition. A complete normal linear space is a Banach space. A complete normal linear space is a Banach space. Banach space. 2.3.7. 2.3.7. 2.3.7 definition. So theorem statement, let infinity be the set of all real bounded sequences Xn is. So supremum of mod xi less than infinity. I is lies between 1 to infinity. All of you write down, record notebook and a manual, example problem, 3 problems. These 3 problems, practice in rough notebook. So let us. So here statement, let infinity be the set of all real bounded sequences Xn is E. Supremum of mod xi 1 less than or equal to I less than or equal to infinity less than infinity. Then show that L infinity is a Banach space with the norm mod x equal to supremum of xi. Xi proof. Proof. We proved L infinity is a normal linear space with norm. Norm of x can be defined supremum of norm xi. So suffix I. So we proved that completeness of L infinity let x power m inner product. Here inner product of x power m, where m equal to 1 to infinity, be any Cauchy sequence in L infinity. Cauchy sequence in L infinity. Since each x power m is a sequence of scalars, x power m is a sequence of scalars, we shall write x power m equal to x1 whole power m, comma x2 whole power m, comma etc. xm whole power m. Let epsilon greater than 0. Let epsilon greater than 0. Let epsilon greater than 0. Each x power m is a sequence of scalars. We shall write x power m that equal to x1 whole power m, comma x2 whole power m. So our x power n whole power m. So let epsilon greater than 0 be given. Then there exists a positive be any Cauchy sequence in L infinity. Since each x power m is a sequence of scalar. So close the door. We shall write. There exists a positive integer n such that L comma m implies norm of x power m minus xl not less than epsilon. That implies maximum of mod x1 whole power m minus xm whole power t comma now x2 mod x2 whole power m minus x2 whole power 1 etc. xm whole power n minus xm whole power 1. So on less than epsilon. Less than epsilon. Less than epsilon. So that implies xi whole power m minus xi whole power n modulus less than epsilon, where I equal to 1 to etc. n. This shows that for fixed I, inner product of xi whole power m, where m equal to 1 to infinity, is a Cauchy sequence of real numbers. Since R is complete, it must be converges to some Zi belongs to R. Zi belongs to R. Zi belongs to R. Zi belongs to R. Let Z equal to Z1 comma Z2 etc. Zn comma norm of x power m minus Z norm equal to maximum of modulus of x1 whole power m minus Z1 comma xn whole power n minus Zn. So on tends to 0 as m tends to infinity. As m tends to infinity. So hence the sequence. Hence x power m tends to z as m tends to infinity. Thus Cauchy sequence, inner product of x power m converges to z, that equal to z1 comma z2 etc. zn. Hence L infinity is a Banach space. Hence proved. This is most important theorem in unit 2 Banach spaces functional analysis. So 2.4.1 definition. What is the definition here? Let capital X comma D comma capital Y comma D dash be two metric spaces. B2 metric. Let there exist a map F such that X tends to X such that 1. So here such that 1 dx comma y that equal to d dash of f of x comma f of y for all x comma y belongs to capital X. Belongs to capital X. So is such that f is a isometry. F is an isometry. From x to embedded from x to f of x, and second f bar of x equal to x dash. F bar of x equal to x dash. F bar of x equal to, that is f of x is dense in x dash. Then we say x comma d can be embedded in x dash d dash d dash. Most important definition here, that x comma d y comma d dash be two metric space. Let there exist a map M x to x such that first condition d of x comma y equal to d dash of f of x comma f of y for all x comma y belongs to capital X. So that is f is an isometry. F is an isometry from x to f of x. F of x. First one. Second one. F bar of x equal to x dash. That is f of x is dense in x dash. So then we say x comma d can be embedded in x dash d dash. Embedded means fixing. So 2.4.2 theorem. Most important theorem. You see, every metric space can be embedded based upon definition. This is theorem. So every metric space can be embedded in a complete metric space, which is called the completion of given metric space. What is the statement? Every metric space can be embedded in a complete metric space, which is called the completion of the given metric space. Is called the completion of the given metric space. Okay. Every metric space can be embedded in fixing in a complete metric space, which is called the completion of the given metric space. That is proof. Here proof is not the property. Here let X be a metric space with metric D. Okay? X be a metric space, metric D. Metric space, metric D. Let B be the set of Cauchy sequences in X. So here definition is 2.3.1 and theorem 1 is 2.3.7 and another definition is 2.4.1. Theorem is 2.4.2. So to definite two definitions, two theorems. Only important problem. Let X be a metric space with metric D. Let B be the set of all Cauchy sequences in X. Next, we now prove that for any Cauchy sequences, X equal to Xn and Y equal to Yn. Limit n tends to infinity. D Xn comma Yn exists. Xn comma Yn exists. So we have D Xn comma Ym less than or equal to D Xn comma Yn plus D Xn plus Ym plus D Yn comma Ym. From this we get, this is nothing but inequality of metric space. What is that? We have D Xm comma Yn less than D of Xm. D of Xm comma Yn double time. So Xn comma Yn. Yn. Xn minus. Xn minus Yn plus D of Yn comma Ym. From this we get modulus of Xn comma Ym minus D of Xn comma Ym modulus less than or equal to D Xm comma Xm comma Xn plus D Yn comma Ym. So this is the metric space inequality. Metric space inequality. Since Xn here, Xn comma Yn are Cauchy sequences. Xn comma Yn are Cauchy sequences. It follows that the Xn comma Ym tends to 0. Since what we are discussing, since Xn comma Yn within the set symbol Xn comma within the set symbol Yn are Cauchy sequences. It follows that D Xn comma Xm within the bracket D of Xn comma Xm tends to 0 as D Yn comma Ym tends to 0 as N comma M tends to infinity. Thus D Xn comma Yn is a Cauchy sequence of real numbers, hence converges. So here converges means near to, the point is near to 0. So diverges means beyond that. So limit n tends to limit D Xn comma Yn exists. So convergence, there is a solution. So exists, we define a relation on B as follows. On B means Banach space as follows. This relation is an equivalency relation. Equivalency relations in relations, functions and relations chapter. So first one is reflexive relation. That is nothing but identity relation, symmetric relation, anti-symmetric relation, and equivalency relation. And equivalency class also here is we have to find it. So equivalency relation. So question here, answer. So here, D x comma n by n exists. We define a relation on B as follows. Means on B means Banach spaces. B means Banach space. So limit extend xn. So equal to sequence means in the section sequence xn equal to sequence yn. It if d xn comma yn tends to 0 as n tends to infinity, it can easily verify that this relation is an equivalency relation. The B means Banach space partitioned. B Banach space is partitioned into two disjoint equivalency classes. Two disjoint equivalency classes. Two disjoint equivalency classes. So now let X cap be the set of all equivalency classes in B. Equivalency classes. We denote the equivalency class to which x equal to xn or x cap to x cap. We define a distance function. We define a distance function. So d on capital X. We define a distance function d on capital X as follows. So d cap x cap y cap equal to limit n tends to infinity dxn comma yn dn dxn comma yn. So then it can be shows that d cap is a metric on x. Metric on x. If x cap represents a Cauchy sequence, x cap represents a Cauchy sequence, no xn. Then for as epsilon greater than 0, there exists an integer neta of epsilon, integer neta of epsilon such that dx cap comma xm star comma xm star less than epsilon for all n greater than or equal to neta of epsilon 1, where xm star represent the sequence xm comma xm etc. xm m comma. So we show that x is complete. We show that x is complete. That implies d cap xn star d cap xn star comma xn cap xn cap less than or equal to d xm star m star minus x m star xm star comma xm cap plus d cap bracket within xm cap comma xn cap plus d cap xn cap comma xn cap less than 1 by m plus d cap xm cap comma xm cap plus 1 by 1. Hence xm is a Cauchy sequence. It follows xn is a Cauchy sequence in x. Cauchy sequence in x. From the inequality, what is that inequality? Before we discuss it, that is metric space inequality. T cap x cap comma xn cap is less than or equal to d cap bracket begin x cap xn star plus a d cap, comma xn star, comma xn cap, xn cap. So it follows that d cap, x cap, comma xn cap, d cap, comma xn tends to 0, as then tends to infinity. Thus x is complete. This completes the proof. This completes the proof. Now, today we are discussing what we discussed. So, unit 2, Banach spaces in functional analysis. So, concepts 2.3.1 definition. A complete normal linear space is a Banach space. Complete normal linear space is a Banach space. So, one theorem. What is the statement? That infinity be the set of all real bounded sequences xn, that is supremum of mod xi less than infinity, 1 less than or equal to I less than or equal to infinity. Then show that L infinity is a Banach space with the norm of x equal to supremum of mod xi. Not xi. So we proved L infinity is a normal linear space with the norm of x equal to supremum of xi. We proved that completeness of infinity. Let inner product of x power n equal to 1 to infinity be any Cauchy sequence in L infinity. Cauchy sequence in L infinity. L infinity. So Cauchy sequence in L infinity, since each x power n is a sequence of scalars. So we shall write x power n equal to x1 whole power m comma x2 whole power m such that xn whole power m. Let epsilon greater than 0 be given. Then there exists a positive integer n such that L comma m greater than or equal to n. That implies norm of x minus x1, norm less than epsilon. So that implies maximum of modulus of xi m minus xi whole power t, x1 whole power t, comma modulus of x2 m minus x2 l, so on xn whole power m minus xm whole power l. So which is less than epsilon. That implies xi whole power m minus xi whole power l less than epsilon. So where I equal to 1, 2, etc. n. This shows that for fixed I, inner product xi m equal to 1 to infinity is a Cauchy sequence of real numbers. Is must R is complete. It is must converges to some zi belongs to none. Let z equal to z1 comma z2 comma etc. zn. Norm of x power m minus z, norm equal to maximum of modulus of x1 whole power m minus zi, comma modulus of xn whole power m minus zn. So tends to 0 as m tends to infinity. Hence x power m tends to z as m tends to infinity. Thus, Cauchy sequence inner product of x power m converges to z, z1 comma z2 etc. zn. Hence L infinity is a Banach space. So second one, most important definition, 2.4.1 definition. So let x comma d, y comma d dash be two metric spaces. Let there exist a map of x to x such that d of x comma y equal to d dash of f of x, f of y, for all x comma y belongs to capital X. That is, f is an isometry from x to f of x. So and to f bar of x equal to x dash. That is, f of x is dense in x dash. Then we say x comma d can be embedded in x dash d dash. Embedded means to fixing. To fix. Theorem 2.4.2 theorem. Every metric space can be embedded in a complete metric space, which is called the completion of the given metric space. Proof 2.4.2 theorem, important theorem. Let X be a metric space with metric D. Let V be the set of all Cauchy sequence in X. We now prove that for any Cauchy sequences, X equal to Xn and Y equal to Yn sequence. Let n tends to infinity, dxn comma yn exists. We have xn comma ym less than or equal to xn minus yn plus d yn xn comma yn d yn yn comma ym. From this we get modulus of d xm comma ym minus d xn comma yn less than or equal to d xm comma xn plus d yn comma ym. So since xn comma yn are Cauchy sequences, so it follows that d xn comma xm tends to 0 and d yn comma ym tends to 0 as n comma m tends to infinity. Thus, d xn yn is a Cauchy sequence of real numbers. Hence converges. So limit d xn comma yn xn comma yn is a Cauchy sequence. Dxn exists. We define a relation on B as follows. B means Banach space. So xn equal to yn. Dxn comma yn tends to 0 as n tends to infinity. It can be easily verified that the relation is an equivalency relation. The B is partitioned into disjoint equivalency classes. Now let X cap be the set of all equivalency classes in B. We denote the equivalency class to which X equal to Xn, X cap to X cap. We define a distance function D on X as follows. D X cap Y cap that equal to limit n tends to infinity, D Xn by 1. Then it can be shows that D cap is a metric on X. If X cap represents a Cauchy sequence Xn, then for as epsilon greater than there exists an integer n meta of epsilon such that d xn comma xm star less than epsilon for all n is greater than or equal to meta of epsilon tends to equation number 1, where xm star represents the sequence xm m tends to xm. We now show that x cap is a complete. So D cap equal to xn star comma xn cap less than 1 by n. Then m comma n large D xn star xn cap less than or equal to D xm star comma xm cap. So that equal to D cap xn cap comma xn cap D xn. So xn cap comma xn cap less than 1 by m D cap xm cap comma xn cap plus 1 by n. So hence xm cap is a Cauchy sequence. Xn cap is a Cauchy sequence. So it follows xn is a Cauchy sequence in X. From this inequality, D cap xn comma xn cap less than or equal to D xn comma xn star plus D xn star xn cap. It follows that D xn x comma xn tends to 0 as n tends to 0. Thus X is complete. This completes the proof. Today what we discussed? Today we are discussing Banach spaces, functional, two definitions and two theorems. What is the definite 2.3.1? A complete normal union space is a Banach space. So theorem 2.3.7 and theorem 2.4.2 most important, and the definition also 2.4.1 definition also most important. Okay. So we'll meet tomorrow, same time.